At the start of 2025, deep computing quietly dropped something wild, a RISC-V mainboard designed for the modular Framework 13 laptop. The first version was rough. It felt more like a Raspberry Pi jammed into a laptop shell than something you'd actually want to daily drive. But now, just a few months later, we've got version 2, the DC-ROMA RISC-V AI Mainboard 2. And this thing, it's a meaningful upgrade. We're talking an 8-core RISC-V CPU, improved integrated graphics, and a 40 TOPS NPU baked right into the silicon. Not only does it run Ubuntu on the Framework 13 surprisingly smoothly, it can even handle large language models like DeepSeek R17B. That's a huge leap from the dev-only curiosity to something that's beginning to hold its own as a proper Linux laptop. And when you pair that with the Framework platform swappable ports, upgradable components, and open documentation, you're looking at something we've never really had before, a completely modular, fully open source laptop from hardware to software to architecture. This still isn't a machine for everyone, but if you're curious about RISC-V, passionate about free and open source software, or just want to see what it looks like when open hardware meets open Linux, this is a ride worth joining. Welcome to Lifting Linux. Now, the logical place to start would be with a quick rundown of what RISC-V actually is and how it stacks up against the x86 or ARM CPU architectures you're probably more familiar with. In short, RISC-V is an open standard instruction set architecture, or ISA, that's completely free to use and customize. Unlike Intel's 86 or ARM's proprietary designs, anyone can build a processor based on RISC-V without paying licensing fees or jumping through corporate hoops. That's made it incredibly popular in academia, IoT devices, and increasingly in experimental desktop and mobile computing. But if you want a deeper dive into what RISC-V is, how it was developed and where it's headed, and how it compares to chips from Intel, AMD, Apple, or Qualcomm, I already covered all of that in my video on the original DC-ROMA mainboard. I spent the first few minutes of that one breaking it all down, and honestly, not much has changed on that front. You can check out that video here. What has changed is pretty much everything else. This second-gen mainboard brings major upgrades across the board, and that's what I want to focus on today. We'll start with the unboxing, go over the updated specs and features, install it into the Framework 13, walk through the OS setup, and then put it to the test, including running a local AI model. So let's kick things off by cracking open the box and checking out what deep computing's been working on. Unlike the first RISC-V mainboard, which I purchased directly from the Framework marketplace, this new DC-ROMA mainboard 2 was sent to me by Deep Computing, and as far as I can tell, it's not currently listed on the marketplace. You'll need to buy it directly from Deep Computing's site. That said, it still arrived in the same sustainable Framework style packaging, all recyclable cardboard and parchment wrap. Out of the box, you'll spot some immediate differences from the original. First, the heatsink has been redesigned. It's larger with a broader heat spreader to cool the beefed up SoC underneath. The chip powering the mainboard 2 is the ESWin EIC7702X, which Deep Computing lists as a RISC-V 64-bit 8-core up to 2 GHz processor. And those 8 cores are based on i5's performance P550, a proper out-of-order Linux class 64-bit RISC-V core. This isn't microcontroller territory. These are real CPU cores with dedicated L1 and L2 caches grouped into clusters that share a larger L3 cache. On paper, the performance class is roughly comparable to older ARM laptop SoCs, think Cortex A75 era, like what you'd find in early Chromebooks or mid-range Android tablets. Not quite Apple Silicon or Snapdragon X levels, but definitely ahead of the Raspberry Pi 3-like experience of the original mainboard. Clock speeds are capped at 2 GHz, and it supports up to 64 GB of LPDDR5 memory soldered directly to the board. Mine is the 32 GB version with 4 8 GB LPDDR5 6400 modules arranged around the SoC. It also supports proper PCIe Gen 3x4 NVMe storage, which is a major upgrade over the eMMC only first gen board. You still get an SD card slot and an eMMC socket, but this now feels like a real laptop platform, not just a dev board squeezed into a framework shell. What really sets the SoC apart is what's built around the CPU. You get an Imagination GPU for desktop graphics and video acceleration, plus a dedicated NPU rated at 40 TOPS for local AI workloads. The marketing materials claim up to 50 TOPS of total AI compute when you factor in CPU plus GPU plus NPU, but the real story here is that you've got legit dedicated hardware for machine learning, vision models, and inference without dumping everything on the CPU. So spec-wise, this mainboard gives you a full 8-core RISC-V CPU, integrated graphics, and a surprisingly capable AI accelerator, all in one board that slots into the framework ecosystem. And now let's talk about fit and finish. The mainboard too drops right into the Framework 13 chassis with no modifications. The form factor is still perfect. That said, there are a few compatibility quirks. Like the original board, this one does not support the newer 2.8K 120Hz display, so I had to reinstall the original 2256 by 1504 60Hz panel. And while it works with the 61 watt-hour battery, it's not optimized for it, so I swapped back in the older 55 watt-hour back for better behavior under load. For wireless, it uses the Intel AX210 Wi-Fi 6E adapter, and it fully supports the Framework 2-watt stereo speakers, audio board, and fingerprint sensor. I haven't tested it with the second gen webcam, but it works fine with the original module. As for ports, you get the same USB-C expansion support as the first gen RISC-V board, though the DisplayPort alt mode has moved to the right-hand side this time. Like before, the board only supports a single display output, so for all my testing, I'm sticking with the built-in screen. There are 3 different storage options you can use to boot this system: the onboard eMMC socket, a micro SD card, or the NVMe M.2 SSD slot. Mine came preloaded with a 64GB micro SD card, but I pulled that out and installed a 1TB Team Group PCIe Gen 3 M.2 SSD instead. But here's where things work a little differently than what you might be used to. Unlike x86 systems, which use UEFI firmware to boot from any attached storage, RISC-V lacks a standardized UEFI implementation, and many RISC-V boards, including this one, don't support booting from USB drives at all. That means you can't just plug in a Windows or Linux installer and go through the setup process like you would on a typical PC. Instead, you need to pre-flash a complete bootable operating system directly onto the storage before installing it into the laptop. Thankfully, the process is straightforward. All you need is another computer with an M.2 slot or a simple USB to M.2 SSD enclosure, which is what I used. After dropping the SSD and connecting it to the Framework 13 before I swapped the mainboard, I downloaded Deep Computing's custom Ubuntu 2404 RISC-V image for this mainboard, then used Etcher to flash the image directly to the drive. Once that was done, I installed the SSD into the mainboard, reassembled the laptop, and powered it on. It booted right into Ubuntu without a hitch. The OS is already pre-configured out of the box. Everything from drivers to display settings was ready to go. The first thing I did was run a full system update. Based on my experience with the first gen board, I fully expected something to break, but this time, nothing did. Everything updated cleanly. That said, performance-wise, it's still not quite on par with the x86 mainboards. Compared to my Ryzen AI setup or even the original 11th gen Intel board, this one definitely feels slower. Gestures and GUI interactions have noticeable input lag, and launching app takes a few extra seconds. But overall, it's a usable experience and a clear step up from the first generation DC-ROMA board. The Ubuntu image provided by Deep Computing is relatively lightweight. Once installed, it expands to just under 50GB of storage and uses less than 2GB of RAM at idle. You may have noticed the system is only reporting 16GB of total system memory, even though this board has 32GB installed. That's because by default, half of the RAM is reserved for the NPU used to run local large language models. You can adjust this in U-Boot depending on your workload. After finishing my LLM tests, I reclaimed a bit more memory back to the system before doing some more benchmarking. As for software, the pre-installed package is set pretty lean. You get a couple of browsers, the LibreOffice suite, a webcam capture app, a few media players, Vim, and somewhat surprisingly, Super TuxKart. While gaming wasn't high on my list for this main board, I did take that for a spin and it ran really well. Beyond that, I installed a few basics like psensor and htop from the standard Ubuntu repositories. The Phoronix test suite was a simple download and install, and I was able to clone and build CoreMark from source with no issues. That said, this isn't a full-fat Ubuntu experience. You don't get the software store, GNOME App Center, or even Synaptic pre-installed, but they're easy enough to add. Once I had Synaptic installed, I was able to find and install the RISC-64 version of GIMP, which launched and ran without many immediately noticeable issues. But here's the deal. You won't find Steam, Discord, or any other Electron-based apps because there simply aren't RISC-V builds available yet. And that brings us to containerized app formats. Oddly enough, Snap isn't included by default in this Ubuntu build. That might sound surprising coming from Canonical, but it makes sense. Snap apps must be packaged for each architecture, and nearly all Snap packages are AMD64 or ARM64, with almost none built for RISC-64. Even if you install Snap Manual, you'll find very few apps that actually run. Flatpak technically could be installed, but the same issue applies. Most Flatpak apps on FlatHub have no RISC-V builds, and app images only function if the developer has bundled a native RISC-64 binary, which again is exceedingly rare right now. And to me, that's exactly the point of this main board. It's not about running your favorite apps out of the box, it's about creating a working RISC-V laptop platform that developers can use to build, test, and publish RISC-64 binaries. It's the missing piece in a RISC-V software ecosystem, a real-world, daily drivable development target that can help push the entire architecture forward. To set the performance baseline, the original DC-ROMA RISC-V mainboard landed somewhere between a Raspberry Pi 3B and 4 in raw performance. It scored about 17% higher than a Pi 3B in the CoreMark integer processing benchmark. The Mainboard 2, on the other hand, scored a CoreMark of 11,049, roughly 109% performance uplift over the first gen board. That result puts it somewhere between a Raspberry Pi 4 and 5, though still closer to the Pi 4 overall in terms of practical CPU performance. For something more real world, I ran a timed Linux kernel compile, and the Mainboard 2 finished it in about 44 minutes. That's 30% faster than the first gen board, but still a far cry from the 8 to 9 minute range you'd see on an Intel N150 or Apple M1. So yes, it's a meaningful upgrade, but we're still firmly in Raspberry Pi class performance when it comes to general purpose CPU workloads. Where things get more interesting is AI inference, because that's clearly where deep computing has shifted its focus with the second generation board. The Ubuntu 2404 image comes preloaded with a DeepSeek R1 7B model, and launching it is surprisingly simple thanks to the built-in browser-based GUI. DeepSeek R1 is one of those verbose chain of thought LLMs that tends to over-explain, overthink, and self-talk its way through an answer. Still, the mainboard held a consistent performance of about 5 tokens per second during inference. For context, that's on par with what you might see from a mid-range CPU-only laptop, but it's noticeably slower than the Apple M series or Snapdragon X class NPUs, which offer significantly higher throughput at similar TOPS ratings. Based on my testing and what I've seen under the hood, I'm fairly confident that the inference stack isn't fully saturating the 40 TOPS NPU, and it doesn't appear to be utilizing the integrated GPU at all yet. And to be fully transparent, while I've built a solid foundation of experience configuring and running AI inference on CUDA and ROCm backends over the past few years, I am not fully up to speed on RISC-V specific implementations of AI tooling and frameworks just yet. Hopefully someone like maybe Wendell from Level 1 Text gets their hands on this board and does a full deep dive into the NPU, drivers, and inference stack. As it stands, the AA capabilities here on an open hardware platform are promising, but for me, What's even more exciting is the potential of this board as a FOSS development platform. There's nothing I'd like to see more than a fully open software stack running on fully open hardware, and the DC-ROMA Mainboard 2 is a real step toward making that dream a reality. As far as power efficiency, this i5 RISC-V SoC still has a long way to go compared to its ARM64 or even x86 counterparts. At idle, the system draws about 25 watts, and under full CPU load, it only climbs to around 31 watts. That's a surprisingly small delta under stress, which suggests the baseline power draw from the SoC, memory, and supporting components is already high, and that power management features like clock gating or deep sleep states aren't fully utilized. Most likely, driver level power optimization for this RISC-V platform just isn't mature yet, especially compared to what you'd find on modern Intel or ARM laptops. Even in suspend mode, the system still draws a steady 4.6 watts, which is far higher than expected and will bleed the battery dry pretty quickly. It's another sign that deep power saving states are either not being triggered correctly or simply aren't supported yet in firmware. Now, I wasn't able to do proper battery testing since my 55 watt-hour battery is already pretty well degraded, but doing the math on that constant 25 watt idle draw, you get a theoretical maximum runtime of just over 2 hours. The fan behavior is another quirk mentioning, which you might have just heard shut off. The fan curve out of the box is extremely aggressive, even though the SoC rarely exceeds 53 degrees Celsius under load. It idles between 47 and 50, and the moment it hits 50, the fan jumps sharply from around 50% to 100%. It's jarring, especially in an otherwise quiet environment. The cooling system is clearly capable, but the lack of ramp smoothing or curve timing gives the system a rough, unfinished feel. Before I wrap this up, I want to be absolutely clear. The DC-ROMA AI Mainboard 2 is not a product for the average Framework 13 user, and it's definitely not an upgrade over any of the existing x86 mainboards, past or present. If you're looking to boost performance, efficiency, or compatibility, this isn't the path. What it is essentially is the equivalent of dropping a Raspberry Pi 4 into a premium Ultrabook chassis, but with a much bigger mission. The Mainboard is built for RISC-V developers, Linux contributors, and FOSS enthusiasts, people who want a portable, bare metal RISC-V development platform that runs a real full-featured Linux OS. And it delivers on that promise far better than the first gen board. We've gone from a proof of concept with training wheels to something that feels much more solid underfoot. Of course, the price reflects its niche appeal. The DC-ROMA AI PC RISC-V Mainboard 2 with 32 gigabytes of RAM and a 1 terabyte NVMe SSD comes in at $659, a recent price bump thanks to RAM pricing. That puts it right alongside mid to upper tier x86 options like the Ryzen AI 7 350 or Core Ultra 7 155H, both of which will absolutely wipe the floors with it in terms of raw performance. But that's not what this is about. This is about freedom. I mean, when you combine the open source hardware of this mainboard, the fully modular design of the Framework laptop, and a Linux OS built entirely on FOSS principles, what you're looking at is something we've been chasing for years, a laptop that's open from the ground up. CPU, mainboard, operating system, and even the physical structure of the machine itself, open, hackable, and evolving in public. And while it might not be ready to replace your daily driver just yet, it represents something far more meaningful, a vision of computing that puts control back into the hands of developers, creators, and users. The DC-ROMA Mainboard 2 isn't for everyone, but it is an essential step forward to a future where computing isn't locked down behind licensing agreements, proprietary firmware, or walled gardens. And in that sense, when paired with the Framework 13, this might just be the most open laptop ever made. Thanks for joining me for this look at the Deep Computing's latest contribution to open hardware ecosystem. If you got anything out of this video, be sure to tap that like button. It really helps support the channel. If you want to see one of my DIY projects using a Framework mainboard, check out this video right here. And if you're into exploring the world of open hardware, Linux, and free and open source software, consider subscribing so you don't miss what's coming next. Until then, thanks for watching, and I'll see you in the next one.